In question 1, we're given the speed time graph for the journey of a car moving in a long queue of traffic on a straight horizontal road. We are told that at time t is 0, the car is at rest at the point A. It then accelerates uniformly for 5 seconds, reaching a speed of 5 meters per second. And then for the next 15 seconds, it's traveling at a constant speed of 5 meters per second. This is the part of the speed time graph during which the car is traveling at a constant speed. And then we decelerate uniformly, coming to rest at point B. Now the total journey lasts for 30 seconds, and we need to find the distance AB. Now we know that the distance is given by the area under a speed time graph, which is the shaded area here. So we're looking at the trapezium. Now base 1 here is 30, base 2 here is 15. So let me write the 15 here, and therefore we can say that the distance AB will be given by 30 plus 15 over 2, so base 1 plus base 2 over 2, times the height of the trapezium, which is the 5 here, so times 5, and this gives an answer for AB of 112.5 meters. In part B, we're asked to sketch a distance time graph for the journey of the car from A to B. So this is the speed time graph we were given. Let's go for the distance time graph. We've got the distance against time. For the first 5 seconds, the car is accelerating. So the distance against time, it's going to be a curve bending inwards. So for the first 5 seconds, this is what's happening here. Then we've got a constant speed between the 5th and 20th second. This means that the distance time graph will be a straight line. And then from the 20th to the 30th second, we are decelerating. So this time, the distance time graph is again a curve, but this time bending outwards, attaining a distance of 112.5 meters by the end of the journey. So essentially, the distance time graph consists of 3 different graphs. At the beginning, we've got the curve bending inwards, then it's a straight line, and then it's the curve bending outwards. In question 2, we need to show all stages of our working and solutions relying on calculator technology are not acceptable, so we need to make sure that we are showing our method clearly here to claim all marks. Now we're looking at a particle moving along a straight line. At time t seconds, the velocity is given by this expression in terms of t, and we are asked to find the acceleration of the particle when t is 4. Well, we know that the acceleration is the derivative of velocity with respect to time. So the first thing to do is write the expression for the velocity in index form. So we're looking at v is 2t minus 7t to the half plus 6. And I proceed, the acceleration is dv by dt. So this is equal to 2 minus 7 times a half t to the minus a half, which simplifies to 2 minus 7 over 2 root t. Now I will proceed to evaluate this when t is 4. So I'm going to say that when t is equal to 4, the acceleration is 2 minus 7 over 2 times the root of 4. Now if I plug this on the calculator, I get an answer of 1/4 meters per square second. We are then told that when t is 1, we are at point x, and when t is 2, we are at point y. Given that the particle does not come to instantaneous rest in the interval 1 to 2, we need to show that xy turns out to be this expression here. So we need to be careful here. The fact that the particle does not come to instantaneous rest, it means we do not have a change in direction of motion, and therefore the distance xy will simply be given by integrating from 1 up to 2 the expression for the velocity. So it's going to be the integral of 2t minus 7t to the half plus 6 dt. Now we know that in integration we're increasing the power by 1, dividing by the new power. So this is giving me 2t squared over 2 minus 7t to the 3 over 2 divided by 3 over 2 plus 6t, and the limits are 1 and 2. Now obviously the 2 with the 2 will simplify out, so we've got t squared minus 14 over 3 t to the 3 over 2 plus 6t, with the limits being 1 and 2. I will proceed by substituting the upper limit to give me 2 squared minus 14 over 3 times 2 to the 3 over 2 plus 6 times 2. And I will substitute the lower limit to give me 1 squared minus 14 over 3 times 1 to the 3 over 2 plus 6 times 1. Remember, this is a show that question. We need to show all the working clearly. If I plug this on the calculator, I'm getting a decimal, which is not enough because I need to arrive exactly at this form here. So let's proceed in treating this on a term-by-term basis. So 2 squared is 4 minus 14 over 3. Now 2 to the 3 over 2 here is 2 to the 3 raised to the half. So it's 8 to the half, which is equal to root 8. So I'm going to write root 8 here plus 12. Now the lower limit substituted can simply be evaluated to give me 7 over 3. So we're looking at minus 7 over 3. And therefore we proceed. 4 plus 12 minus 7 over 3 is 41 over 3. And then I'm going to split the root 8 into root 4, root 2. And obviously root 4 is 2. So we're looking at 41 over 3 minus 28 root 2 over 3. I will proceed in factoring out the third. So we're looking at the third brackets 41 minus 28 root 2 meters as required. In question 3, we've got the particle P moving on a smooth horizontal surface under the action of two forces. Now we're given that the mass of P is 2 kilograms. The two forces are 2I plus 4J and Ci minus 2J. C is a constant. And the magnitude of the acceleration of P is root 5 meters per square second. And we need to determine the two possible values of C. Well, I will start by considering the resultant force acting on P, which is simply given by the sum of the forces acting on P. So I will be doing here 2, 4 plus C negative 2, which simplifies to 2 plus C 2. And then we know that force is mass times acceleration. Now, since I'm given the magnitude of the acceleration and not the acceleration vector itself, I will proceed by taking the magnitude of everything. So the magnitude of F here is equal to mass times the magnitude of the acceleration. Now the magnitude of F is given by Pythagoras. So we're looking at 2 plus C raised to the power of 2 plus 2 squared and all under a square root, being equal to the mass of 2 times the magnitude of the acceleration, which is root 5. So the first thing to do is square everything, taking me to 2 plus C raised to the power of 2 plus 2 squared is equal to 20. And I will proceed by expanding. We get 4 plus 4C plus C squared plus 4 is equal to 20. And if I collect everything on the left hand side, we get C squared plus 4C minus 12 is 0, which factorizes into C plus 6 and C minus 2. Now we know that either C plus 6 is equal to 0, or alternatively we've got C minus 2 is equal to 0, and therefore C is negative 6 or C is equal to 2, the two possible values for C. In question 4, we're given a car towing a trailer along a straight horizontal road. Now the mass of the car is 800 kilograms and the mass of the trailer is 600 kilograms. The trailer is attached to the car by a tow bar here, which is parallel to the road and parallel to the direction of motion of the car and the trailer. Now the tow bar is modeled as a light rod. The resistance to the motion of the car is modeled as a constant force of magnitude 400 newtons. The resistance to the motion of the trailer is modeled as a constant force of magnitude R newtons. The engine of the car is producing a constant driving force of 1740 newtons, and the acceleration of the car is 0.6 meters per square second, while the tension in the tow bar is capital T newtons. And using the model, we need to show that capital R is 500. As always, I will start by adding all the forces acting on the diagram here. So we've got the car and the trailer. We've got the driving force of 1740 newtons acting on the car, pointing along the direction of motion. And then we've got the resistance to motion, we've got the 400 newtons resisting motion of the car and the R newtons for the trailer. Now we also have the tension in the tow bar, so the trailer is feeling the tension acting to the right, while the car is feeling exactly the same thing but in the opposite direction. And we know that overall we're accelerating to the right with an acceleration of 0.6 meters per square second. We are trying to find R here, so I will be considering the car and the trailer together, which means that forces acting to the right, which is the 1740, minus forces acting to the left, which is the 400, and the R is mass times acceleration. Notice here that the tension here is gonna cancel out. So all in all, we're looking at 1740 minus the 400 plus R being equal to the total mass of 800 plus 600 times the acceleration of 0.6. So we've got 1740 minus 400 minus R being equal to 840, and therefore we've got 1340 minus R being equal to 840, which leads to R being equal to 500 as required. In part B, we're asked to find the value of capital T. So going back to the diagram here, I could highlight here, these are the forces acting on the trailer, and over on the right hand side, these are the forces acting on the car, and I could be considering either the trailer or the car to determine the value of capital T. I will start by considering the trailer. We've got forces acting to the right, which is the capital T, minus forces acting to the left, which is the capital R, is equal to the mass of 600 times 0.6. Well, we know that R is 500, so T minus 500 is equal to 360, which means that T is 860 newtons. Alternatively, I could have considered the car. So looking at the car, we've got forces acting to the right minus forces acting to the left is mass times acceleration. So this time we've got 1740 minus the resistance to motion of 400 plus the tension T being equal to the mass of 800 times the acceleration of 0.6. So we're looking at 1740 minus 400 minus T is equal to 480, and therefore 1340 minus T is equal to 480, which again leads to T being equal to 860, and therefore the two approaches give exactly the same answer as expected. Now at the instant when the speed of the car and the trailer is 12.5 meters per second, the tow bar brakes. The trailer moves a further distance d meters before coming to rest. The resistance to motion of the trailer is still modeled as a constant force of magnitude 500 newtons, and using the model we need to show that after the tow bar brakes, the deceleration of the trailer is 5/6 meters per square second. So looking at the diagram once more, once the tow bar brakes, the car moves out of the picture. We've got the trailer moving to the right, so the direction of motion is to the right, so the acceleration is always pointing along the direction of motion, and therefore I can apply F equals ma here. We've got forces acting to the right, and we've got no force acting to the right, minus forces acting to the left, so 0 minus 500 being equal to the mass of 600 times the acceleration A. So we're looking at minus 500 being equal to 600A, which means that minus 5/6 is the acceleration. However, the question is asking for the deceleration. The deceleration is the negative acceleration. So all I have to say here is that the deceleration is 5/6 meters per square second as required. We're then asked to find the value of D, and I will be using Suvat equations here because the trailer is experiencing a constant deceleration. So I'm going to be using here V squared is equal to U squared plus 2AS. We know that the final velocity is 0 because the trailer is coming to a rest. So 0 squared is equal to the initial velocity of 12.5 squared plus 2 times the acceleration of negative 5/6 times D. So we're looking at 0 being equal to 156.25 minus 5/3 D, and therefore 5 over 3 d is equal to 156.25. Now if I divide both sides by 5 over 3, we get that d is equal to 93.75 meters. It's okay to keep your answer to 4 significant figures. We haven't used g here to be 9.8, so no need to stick to the 2SF or 3SF. And also be careful, if you end up with S being 93.75, you will be penalized because the question is asking for the value of D, so we always need to adjust to the letter that is used in the question. In reality, the distance d meters is likely to be different from the answer found in part D, and we need to give 2 different reasons why this is the case. So looking at the model itself, we are assuming that the resistance to motion is a constant force of magnitude 500 newtons. So we need to be very careful here. A very common answer would be to refer to the air resistance. However, this will be penalized because the question is speaking for the overall resistance to motion. So this could include air resistance. So we cannot mention that air resistance was neglected, but we could certainly challenge the fact that the force is constant. So the first thing to say is that resistance to motion is unlikely to be constant. And the second point to raise is that the trailer may not continue moving in a straight line, and therefore we expect the actual distance d meters to be different from the one calculated here.